Thank you. So I would like to thank the organizers who prophetically organized this conference in the virtual or semi-virtual format well before the onset of pandemic. I will speak about the work of Ilya Dumanski and Evgeny Feigin about the algebraic description of some global sections of line bundles and Schubert varieties. So probably it will be the most elementary talk at this conference. And the first half, anyway, will be a survey of well-known results. So let's start with the most classical setup. So we'll have a complex simple Lie algebra and the corresponding Lie group, the simply connected form. Then we'll use its flag variety and Schubert varieties and finite dimensional simple modules. So we'll study the Demazure modules. What are they? We'll take an extremal vector in this simple G module and consider the Borel submodule generated by this vector. So for example, if this is the highest vector, then it will be just one-dimensional Borel submodule. And if this is the lowest vector, it will be the whole irreducible G model restricted to the Borel subalgebra. Now, geometrically, the irreducible representation itself is realized by Borel-Weyl theorem as dual to the global sections of some dominant line bundle on the flag variety, and the Demazure model is realized as dual to the sections of the same line bundle on the corresponding Schubert variety. It was described by Tony Joseph explicitly as a cyclic module over universal Weyl algebra of Borel, given by certain relations. Three types of relations. The first one is very evident, just the kernel of the character from the Cartan subalgebra. And then this generating vector is killed by the positive root vectors such that W inverse of this root stays positive. And if it stays, if it becomes negative, then it is killed by an appropriate power of this root vector. For example, if our W is the longest element, so we generate our Demazure module from the lowest weight vector, then this is the usual Harishchandra relations for the model as the model over n plus. Okay, then Olivier Mathieu noticed that the same description holds true for arbitrary Kac-Moody Lie algebra, only we have to be a little bit more careful with the second portion of relations, just because there are some multiplicities of positive vectors. And we will be most interested in the case of affine Lie algebras. So the extensions, central extensions, and the energy operator extension of the loop algebra. And we will consider Demazure module submodules in the integrable level 1 modules, most of all. So these are dual to the global sections of the very ample determinant line bundle on the affine Grassmannian. More precisely, we will need, though our group G is simply connected, we will need now its adjoint group. And then the affine Grassmannian has a few connected components numbered by the co-weight lattice modulo of the co-root lattice. And we will consider the sections over various connected components. They will give various integral models of level 1. Now, the extremal weights of these models will be numbered by the orbit of the affine Weyl group, more precisely the extended affine Weyl group in this case. But this is a very irregular case, parabolic case, so that the highest weight vector has a big stabilizer, and so the orbit of this extended Weyl group is the quotient model of the finite Weyl group, and this is the co-weight lattice of the adjoint group. So note that while in the finite dimensional case the Demazure models were naturally numbered by the weights, the extremal weights, now they are naturally numbered by co-weights. And again, geometrically, they are just global sections of spherical affine Schubert varieties numbered by dominant co-weights. One special feature in this case is that there are models not only over the Ivahori positive subalgebra, but over the whole parabolic or parahoric current algebra. Okay, so if we still want to describe them in terms of weights as opposed to co-weights, then we will need to use a certain map from co-weights to weights that corresponds to the level 1, that is some minimal integral valued symmetric invariant bilinear form. So we'll view it as a map from a co-weight lattice to the weight lattice of the simply connected group. Otherwise, it will be rather rational. And in case our group is simply laced, then this is just the tautological bijection between co-weights of the adjoint form and weights of the simply connected form. Okay, so now if we want to describe the affine weight, say the lowest affine weight of the Demazure module, then, well, its central component is 1, it's of level 1, but the finite component is obtained via this bijection, namely we take the lowest weight in the finite Weyl group orbit of this bijection, iota of lambda. And if we want the highest weight component, then its finite part is just 0 if we are in the main connected component of the Grassmannian. In other words, if our co-weight actually lies in the co-root lattice, or else it is the minuscule representative of iota of lambda if it's in some other connected component. Okay, we will also need some global counterpart of our Demazure models. So Demazure models are, in a sense, some local guys, and we'll need the global Weyl models. In fact, they are given by the very similar relations, only of the loop flavor. So the Demazure models were given by relations written down in Kac-Moody setup, but the affine Lie algebra also has another loop presentation, and the Weyl model has relations in this loop presentation. So it's again the kernel of the same character, but then the augmentation ideal of the whole universal labeled algebra of currents into the whole positive subalgebra. And for the negative finite generators, you again have appropriate powers. In other words, this global Weyl module is just the maximal integrable quotient of the induced character. So you take the currents of nilpotent subalgebra, add the finite Cartan, take one-dimensional representation, induce it to the whole current algebra, and take the J-integrable quotient. Okay. Now the relation between the local Demazure models and global Weyl models is most explicit for the simple laced case, and the fundamental highest weights or co-weights, they correspond under this iota bijection. Namely, the Weyl model is obtained just by spreading the Demazure model over the affine line. So we take this local finite dimensional Demazure model corresponding to the fundamental weight or co-weight, multiply it, tensor it with the polynomial algebra, and define the action of the current algebra just by Newton binomial formula, and we obtain the global Weyl model. Now, if we're interested in other weights, not necessarily fundamental weights, then there's a similar story, and to formulate it, I will need some analog of polynomial algebra we had on the previous slide. How does it arise? Just from the definition of the global Weyl module, it is acted upon by some very big commutative algebra, the universal enveloping algebra of Cartan, current algebra, just by carrying it through the generator. But in fact, for a given weight theta, the action of this big algebra of infinite functional dimension factors through a quotient of finite functional dimension, which depends on the highest weight theta. Namely, it's some partially symmetrized polynomial algebra. You expand the highest weight into sum of fundamental weights, and then you take the product of the corresponding symmetric powers of a fine line, and the functions on this product, in other words, on some configuration space, colored configuration space of a fine line, will act on the Weyl module. And the key result here, due to Littleman and Fourier, or maybe other mathematicians in some particular cases, says that this action is free. Okay, now let's consider again the case when G is simply laced and our highest weight theta arises from some highest co-weight. Then we can consider the colored configuration space for this co-weight, and the local Demazure module is just the fiber of this global Weyl model at 0. So this is similar to the relation in the fundamental case we had in the previous slide. And again, there is a way to reconstruct the global Weyl models from local Demazure models in this simple laced case. And it works as follows. We decompose our weight lambda into the sum of fundamentals once again. And then we consider again the spreadings of the corresponding fundamental Demazure modules over the affine line. And then we take their cyclic product. So the cyclic product of two cyclic modules is a submodel of their tensor product generated by the product of cyclic vectors. If you wonder what is the cyclic vector of the Demazure models spread out over the affine line, it is just the cyclic vector of the local Demazure model, tensor constant function 1.
Misha?
Yes.
Why is it necessary? Is it necessary to have G simply laced in those theorems? What goes wrong?
Absolutely, yes, absolutely. I will tell later on what happens with the non-spliced case, but in the non-spliced case, you will not even be able to realize fundamental weights as images of any co-weight at all. Right, so this iota map will be not surjective. It will not cover all the fundamental weights. Okay, so now we want to describe some geometric realization of these global Weyl modules. In fact, one realization was known for some time, namely, it is sort of semi-infinite Borel-Weyl theorem. They are dual to global sections of some line bundles on the semi-infinite flag scheme of infinite type. But I will speak about some other new geometric realization as global sections of some finite dimensional schemes. So namely, there will be sort of Schubert varieties in Beilinson-Drinfeld Grassmannian. So I will recall what is Beilinson-Drinfeld Grassmannian, first of all. So first of all, it depends on some a positive number k. And in case of k equals 1, it will be almost the usual affine Grassmannian. But for bigger k, you first specify a k-tuple of points in the affine line. You can do this for arbitrary curve, but for Weyl models, we'll need only the affine line. So you take a k-tuple of points, torsor over the adjoint group on the affine line, and its trivialization outside of these points. So if k equals 1, then the global coordinate t on the affine line gives rise to identification. The first Beilinson-Drinfeld Grassmannian is just the direct product of the usual affine Grassmannian and the affine line. Now, the main property we'll need of the Beilinson-Drinfeld Grassmannian is the factorization property that says that the fiber of this Beilinson-Drinfeld Grassmannian over a divisor, which is disjoint union of two smaller divisors, is just the product of the corresponding fibers of smaller Beilinson-Drinfeld Grassmannian. So in particular, it means that away from all diagonals, the fiber is canonically identified with the power, kth power of the affine Grassmannian. But then over the diagonal, for example, when all the points collide at 0, this is just the Grassmannian itself. So it looks, if somebody sees it for the first time, it looks as a contradiction, but it is true. And what happens is that Grassmannian is an int variety, the union of Schubert varieties. And when you do it at the level of finite dimensional Schubert varieties, when they merge towards diagonal, the labels just add. So ger lambda times ger mu fuses into ger lambda plus mu. Now we will also need the action of some group there. As on the usual affine Grassmannian, there is an action of the loop group, or at least of the current group, the formal Taylor series with coefficients in G. And this Beilinson-Drinfeld Grassmannian is acted upon by a sheaf of groups, which behaves very similarly, so it factorizes. Namely, its fiber over the divisor without multiplicities is the kth power of the current group, and the fiber over diagonal is just the first power of the current group. And for formally, it's just the inverse limit of the quotients of polynomials over polynomials vanishing at these points to big degree. And there is an obvious homomorphism from the polynomial group to this to the global sections of this completed group, just taking completion at the corresponding points. well, this is sort of embeddings of rationals into adels. Okay, so now we are ready to describe the global Schubert varieties in the Beilinson-Drinfeld Grassmannian. So we take arbitrary dominant coweight, decompose it into the sum of fundamental coweights, and d is the total degree, the sum of all coordinates, this is the number of points for the Beilinson-Drinfeld Grassmannian. So when all these points are distinct, then we just take the direct product of the corresponding fundamental Schubert varieties, and then we just take the closure of this, so we fuse them over diagonals. And this is the closure of some orbit of our group in the generic fiber of the configuration space. Also, we'll need some partial symmetrization of this because we had d many points, but over them we had the products of fundamental Schubert varieties, and among them di were the same Schubert varieties, so that the renumbering of these points, the symmetric group acts there, and we can symmetrize with respect to this group and obtain this partially symmetrized Beilinson-Drinfeld Grassmannian over the configuration space, the colored configuration space A lambda. So once again, the fiber of this closure over the diagonal point will be just the usual Schubert variety in the affine Grassmannian G lambda. Now, the determinant line bundle, it lives on the whole Beilinson-Drinfeld Grassmannian, and it is covariant with respect to these permutations. So it descends to a relatively ample determinant line bundle on our global Schubert variety. The action of our completed group also descends to the action of this partially symmetrized Schubert variety. And finally, if you remember what we started with on this slide, there is a homomorphism from the polynomial group to the global sections of this completed current group. So it acts via this homomorphism on the global sections on the global Schubert variety. Just I wonder if I have to stop in 25 minutes. It's absolutely fine with me not to stop.
Yeah, it would be good to take a break, maybe now or in a couple minutes, whenever is a good time.
So then now it is a good time.
Okay, great.
Questions. Yeah, Misha, I have a question.
Yes.
Is the implicit claim that these global Weyl modules are sections of a determinant line on a local semi-infinite flag manifold? Like, if we took an analytic model, should I be able to get these global Weyl modules?
Yes. So I said that there is this semi-infinite flag scheme. So it's lately studied in much detail by Shiu Kato. Yes, so in fact, the whole thing is rather in the scheme of infinite type, but it contains some sub-scheme of infinite type. Yes, so you understand what I'm talking about.
Yeah.
And then you take the global sections of line bundle over this scheme, and you get the dual global Weyl model.
I see.
And this may be called semi-infinite Borel-Weyl theory.
Mm-hmm.
So it was proved by Braverman some 5 years ago or more. But this is something different. In particular, in the next slide, we'll see some dualization, and this dualization is different. So there are, so to say, two notions of dual global Weyl modules.
I see.
So are you going to
Yes.
are you going to discuss the relation between that and this Borel-Weyl on the affine Grassmannian?
Unfortunately, I don't understand this relation. I would like to, but I have nothing to say, unfortunately. Yeah, there is some mystery there, but I don't understand.
Very, very naive question. So,
Yes.
usual Demazure modules, I guess they can be realized as sections of a line bundle on the closure of a Schubert cell.
Oh, yes.
And so is there a global analog of, a fine analog of that?
You mean for affine Demazure modules?
Yes.
Oh, yes. And in fact, we even discussed this in the very beginning.
Right. So that's it's a way to think about this construction. Okay.
But this is local, I think. And now we're discussing the global analog.
Right. But so there is also a global analog, which is what you are explaining.
Yes, so just the very next slide will be the global analog of this local theorem of yours.
Thanks.
I guess we can probably resume now.
Okay.
I think it's been 5 minutes. If you're ready, Misha, you can start again.
Okay. Okay. So on this slide we have the definition of some global spherical Schubert varieties in the Beilinson-Drinfeld Grassmannian. In fact, there are more general global spherical Schubert varieties, namely these ones on this slide. They correspond to decomposition into fundamental co-weights. In general, you can have decomposition into arbitrary co-weights, but so far we only just have the ones corresponding to decompositions into fundamental co-weights. So away from all the diagonals, well, all the points are distinct, we have the products of fundamental Schubert varieties in the usual affine Grassmannians. And we're interested in the global sections of the determinant line bundle over these global Schubert varieties as modules over the polynomial current Lie algebra.
Sorry, Misha, can I ask a quick question? Sorry, going back to the previous slide. So this fact that the fiber over 0 is actually Gur lambda and it's reduced.
Yes.
Is that that's a theorem of Shin-Ren-Zhu, or do you have some other easier argument in mind?
I think this is actually a theorem of Fourier and Littleman. I think Shin-Ren-Zhu actually refers to them.
Yeah, okay. But so it uses these.
Yes,
it uses the stuff from before, basically. Yeah.
Oh, absolutely, yeah. In fact, everything will somehow use the fundamental work of Fourier and Littleman. All the arguments rest on this, unfortunately. Okay, so yeah, for example, this very first claim of this theorem uses the full force of Fourier-Littleman. So it says that the global sections of the determinant line bundle over this global Schubert variety is a free model over the functions on the base of this configuration space. And then we can consider the dual module, and then this admits an algebraic description. Namely, this is the cyclic product of fundamental local Demazure models spread out over the affine line. And this cyclic product, we will call it the global Demazure module. So once again, this global Demazure model is dual to the global sections of the determinant line bundle, and dual in the sense that it's over the functions on the configuration space. Okay. In particular, if our Lie algebra is simply laced, then we know that this cyclic product is nothing but the global Weyl module, so it corresponds with the global Demazure module. But this will not be true in the non-simply laced case. Okay, now we may be also interested in the higher level. And then for local Demazure models, it is very straightforward. So the local Demazure module of higher level R is just the cyclic rth power of the corresponding local Demazure module at level 1. Okay, and similarly, if we consider the global sections of the of some power, rth power of the determinant line bundle over this global Schubert variety, then again it is a free module over the functions on configuration space, and the dual model coincides with the global Demazure model of higher level. That is nothing but the cyclic product of Demazure modules over the higher level spread out over the affine line. So it's all very similar to the level 1 case. Okay. And now we will study the most general spherical Schubert varieties that are related not necessarily to decomposition into fundamental co-weights, but into decomposition into arbitrary co-weights. So they all appear as the closures of our completed current group in the generic fiber over the Beilinson-Drinfeld Grassmannian. And so we fix a decomposition of our dominant co-weight into arbitrary sum of dominant co-weights like this. And before I describe these more general global Schubert varieties, I will describe the base in the configuration space over that it will live. So I will need all the strata of the colored configuration space. So I will describe them in the following way. First of all, this decomposition of lambda into sum of dominant co-weights gives rise to the addition morphisms from smaller configuration spaces that are product into a lambda. And then each of the factors contains the smallest diagonal stratum, the diagonal stratum, isomorphic to the affine line itself. And now the closed stratum in the colored configuration space is just the image of the product of these diagonals. So there is a finite morphism, and this is the image of this finite morphism, closed stratum. But it is also a closed stratum in the configuration space, so we have a surjective morphism from the polynomial algebra of functions on this configuration space onto the functions on this stratum. And on the other hand, the function of this stratum is a subring in the ring of functions onto this affine space. Okay, so it is somehow squeezed in between two polynomial algebras, and it can be described very explicitly inside this polynomial algebra Namely, it is generated by some weighted power sums. Well, for example, in case of SL2, when all the lambdas are fundamental co-weights, then it will be just the usual power sums, and they will generate the usual symmetric polynomials. Okay. Now there's an interesting algebra of functions onto this on this stratum. So as you see, it's usually not normal, and on the other hand, it is often Cohen-Macaulay. So why the question about Cohen-Macaullayness is interesting? Because these algebras, just for SL2 case, they appeared in the work of Alexander Veselov and his collaborators on the quantum Colliger Moser-Sutherland integrable systems. Namely, these algebras arise as the algebras of integrals of motions. And they're also called algebras of quasi-invariants. So they're not quite symmetric algebras, but up to some high order of vanishing at the diagonals. This Cohen-Macaulay property just means that this algebra of quasi-invariants is free over the algebra of invariants. Okay. Now, if I consider the local Demazure modules and I spread them out over the affine line, and I take their cyclic product, as I used to do in the fundamental case, then again, this cyclic product will be equipped with the commuting action of this big polynomial algebra, universal developing algebra of the Cartan current algebra. Again, the action of this big algebra will factor through the action of some finite functional dimension quotient. And this quotient will be nothing but the algebra we discussed on the previous slide. Okay, so it was always the polynomial algebra in the classical Fourier-Littleman case, or when lambdas were fundamentals, but in general, this may be a rather complicated algebra, not polynomial anymore. Okay, now I can finally formulate the notion of the most general spherical Schubert variety in the Beilinson-Drinfeld Grassmannian. So again, when the points are distinct, I place the arbitrary Schubert varieties over those points, and then I take the closure or fusion of them over the diagonals. So in particular, the diagonal fiber will be, again, the lambda, where lambda is the sum of those lambda i's. Now the corresponding Schubert variety will be just the base change of the previous Schubert variety to this closed stratum. Okay, so we discussed in the very beginning of this second part of my talk, we discussed the global Schubert varieties over the configuration space, and then I just restrict this Schubert variety to this closed stratum, and I obtain the most general partially symmetrized Schubert variety. Okay, so now it only remains to describe the global sections of the determinant line bundle over these Schubert varieties. It's very similar to what we had in the fundamental case, namely the global sections of the determinant line bundle, or in fact any power thereof, again is a free module over this funny algebra, the functions on the closed stratum. And the dual module over these functions is again the cyclic product of the local Demazure models spread out over the affine line. That is by definition the global Demazure module of level R. And if I'm interested in the sections over non-symmetrized Beilinson-Drinfeld Grassmannian stratum, then they are just obtained by the base change from this funny algebra to the polynomial algebra. And finally, it implies that the symmetrized global Schubert variety is just the projective spectrum of the direct sum of global Demazure models over all levels. And I think this is all I wanted to say. Thank you very much.
Okay, are there any questions for Misha?
Sorry, so why is it important that this is a free module? So how to think about this?
Well, otherwise, we could not really take the dual or well, to compute anything about it. For example, this way we can compute its character just as a product of the character, the zero fiber, that is local Demazure model, and the character of this algebra.
And then how can one, how does one prove that it is a free?
So we have to compare the dimensions at all the points, and this goes back to Fourier-Littelmann, unfortunately. So it's some technical, explicit computation using crystals. In fact, those models are also realized by Nakajima or Varagnola in the equivariant cohomology of quiver varieties, and then it is clear that they are free over the equivariant cohomology of the point.
Mm-hmm.
So from this point of view, yes, it's clear geometrically, but then somehow you still have to identify this definition with the classical definition by generalized relations, and then you cannot avoid this argument of Fourier and Littelmann. So it's really the base of everything.
And these Frobenius splitting methods, they don't help?
At least I don't know why. Maybe it does, but I just don't know. Maybe you can explain to me how it.
Okay, maybe I just will ask one question about the last statement D. So basically you gave a construction, kind of new construction of Beilinson-Drinfeld Grassmannian.
In a sense, yeah, if you want, yes.
If
you are satisfied by this definition of global Demazure modules as cyclic product, because it's not really by generalizations and relations, yeah. It's a sort of subquotient, right?
Mm-hmm.
You take it as a product which is given by explicit generalizations and relations, but then inside you take something which is generated by the cyclic, by the product of cyclic vectors. So you don't have explicit relations for this. So maybe
I want to ask if there is a similar construction for other curves, for global Grassmannian for other curves. So this is just for
yeah, it's interesting, but I don't know. Say for elliptic curve, I don't know.
Thanks.
Thank you.
And there's a question from Yu Feng. Yes, could you please give an application of the global Demazure modules?
Well, I'm ashamed that I don't know such an application, but what is worse, I maybe don't really know application of the usual local Demazure modules. Maybe Fan can give me as an example an application of the usual local Demazure modules. What is considered as an application of them? Maybe again an explicit projective embedding of Schubert varieties. Maybe this. I don't know.
I don't know.
Pardon me? Yes? I don't hear you.
I don't know. I don't know even any application for the local Demazure module. So.
Okay.
And Oscar has a question. Do you want to go ahead and ask it, Oscar?
Okay, let me do that. So is there some analog of Shinwen's construction of this Frankel-Katz-Siegel isomorphism to a lattice vertex algebra in Sobel case?
Even over the curve A1.
Yeah,
right?
exactly. Like, can you do anything like that? Like replace the sort of prefix points by some sort of global affine?
No, somehow we're thinking about it, but not yet.
Okay.
I can say nothing useful at the time. Sorry.
Well, about the application of global Demazure modules, I can say that they actually first appeared as they are homogeneous components of the coordinate ring of the arc space of the Veronese curve. And that's for SL2. And more generally, if you consider a semi-infinite Fleck variety and embed it with respect to semi-infinite Flecker embedding, but then you can compose it with Veronese embedding. So it's embedding to some other big projective space. Then the coordinate ring will be the sum of duals global Demazure modules.
But that's for higher level, right? For higher level.
Yeah. If you take Veronese curve of degree L, then you'll get global Demazure modules of level L.
Mm-hmm.
Yeah, in particular, if you take just a constant map, so which can be considered as Veronese map of degree L, of degree 1, then you get in just global Weyl modules.
Thanks.
And Rekha Biswal has a question. Do you want to ask your question, Rekha Biswal?
Yeah, so in part B, the D of R comma lambda bar, whatever you have written, that is tensor product, but that is true only when these Demazure modules are actually coming from irreducible integrable modules of highest weight R times lambda naught, where lambda naught is the fundamental weight corresponding to the 0th node. But is that a similar kind of result true for arbitrary Demazure modules in level R integrable irreducible highest weight modules?
I'm sorry, I didn't
yeah,
get
so
you. Maybe you can repeat.
So in part B of your theorem, you write that D of R comma lambda bar is equal to this fusion product of this D of R, dr lambda 1 up to dr lambda k, right? That is true only when these Demazure modules are actually coming from irreducible integrable highest weight modules of level R, and the highest weight is R times lambda naught, where lambda naught is the fundamental weight corresponding to 0th node. In fact, one can take lambda I, where lambda I is corresponds to the fundamental weight corresponds to the ith node, but not for arbitrary weight. So this, the equality which you have written, that is not true for arbitrary Demazure module of level R, rather for very special.
No, you don't multiply the finite component lambda by R. You just take the level R, the generator K acts by R, but the finite cartan acts by lambda. So it's among the parabolic, among the spherical Demazure models, these are most general.
I think Misha, she's asking about non-spherical case, like when it's not.
Ah, I see. But
Exactly. That's the question. Yes.
About non-spherical, I have nothing to say at the moment.
Yeah, because for spherical ones, this is the equality which you have written. That's very easy to see. But for non-spherical, it's not actually. This is not true. That you cannot write it as tensor product or fusion product, whatever it is. So that's why I was wondering if similar kind of theorem can be written out for arbitrary Demazure modules, not just spherical ones.
No, for arbitrary, I don't know.
And do you have any further speculation on the question I asked earlier about the relation between this and sections of line bundle on the semi-infinite flag variety?
No, somehow I'm confused because the duality is different. You see, the sections over the semi-infinite is the dual global Weyl module, but dual in the different sense. It's not over this algebra A lambda, but just over complex numbers. So the global sections are rather different. So maybe I don't know. You take the global sections over the semi-infinite manifold or the Beilinson-Drinfeld manifold, and then you dualize them in different sense, and they coincide. But before
right,
this...
and yeah, maybe I should repeat that global Demazure modules of higher level, they appear not as sections of some line bundles over semi-infinite flag variety, but as coordinate rings of semi-infinite flag variety. If you embed it not just with respect to usual Drinfeld-Plucker embedding, but you compose this Drinfeld-Plucker embedding with the Veronese curve of degree L at each projective space. Then the coordinate ring of these embedding is precisely the sum of global Demazure modules of level L, where L is the degree of the Veronese curve. Yeah, and dual with respect to C, not with just numbers, not with respect to these highest weight algebra.
Yeah, so what I was saying was only for level 1.
Are there any other questions for Misha?
I have a question. So higher level, is any relation of global section and the T fixed point groups, T fixed point scheme in high level?
No, I not that I know of. I mean, just for projective space, yeah. If you take say O of 1, then when you restrict to the T fixed points on the projective space, then it's an isomorphism. But if you take O of 2, then it is not. And what is the relation? I have no idea. I don't know any relation whatsoever, unfortunately.
Yeah, let's thank Misha again.
Thank you.